All right, now that we've learned a little bit about the kinetic molecular theory and about heat and temperature, let's look at states of matter and how they differ from each other. This is still part of the kinetic molecular theory because we're looking at these particles that are constantly in motion. So, solids have very low kinetic energy. Remember, kinetic energy is related to speed. So what I mean by this is that particles are vibrating, but they're not moving around. They're just vibrating in place. Solids have a fixed shape. It's sometimes called a defined shape. They don't change their shape the way that liquids and gases do. Similarly, solids have a fixed volume. You can't really pressurize them and change their volume. So this picture here is what we call a particle spacing diagram because it shows how closely together or how far apart particles are spaced from each other. And you can see that the particles in a solid are packed fairly closely together. And sometimes you'll see, kind of like in a cartoon, kind of quotation marks to show that these particles are moving. Particles are always in motion except at absolute zero, but they are just vibrating. They're just kind of vibrating in place. That makes them different to particles in a liquid because particles in a liquid have a bit more kinetic energy than the particles in a solid had. They still have a low kinetic energy, but they are moving a bit more because these particles can actually move around. They're not just vibrating in place. They can actually flow from one area of a container to another. But they are still close together. Liquids, as hopefully you're familiar with, do have a variable shape. Whatever container you pour them into, they take the shape of that container. But they still have a fixed volume. Liquids are not easily compressible. They have the same volume no matter how much pressure you put on them. Gases, on the other hand, have high kinetic energy, and so when we represent these in their particle spacing, we usually draw big arrows to represent their high speed, and they're like bouncing off the walls of the container here. High kinetic energy, this means they're moving quickly. Because they're moving so quickly, the particles separate from each other, they're spaced apart, and they can move rapidly throughout the entire container. Because they can move throughout the entire container, well, again, they have a variable shape. So whatever container you pour them into, they take the shape of that container. But also they have variable volume. So they will take up, these particles will take up as much space as you give them. So think of some sort of aerosol can where you've got the pressure, high pressure gas inside the can, and all that gas fits inside that can. But as soon as you give that gas an escape route, as soon as you push the nozzle on the aerosol can, the gas escapes and will fill up an entire room. So that's what we mean by having a variable volume. Phase changes. Substances don't necessarily just stay as a solid or a liquid or a gas. They can change between the states. And so it's important to have names to describe each of those physical changes. These changes can be exothermic or endothermic, and it's color-coded on here whether it's an exothermic change or an endothermic change. Remember, in an exothermic change, heat exits the substance, and in an endothermic change, heat enters the substance. So hopefully that makes sense to you. How do you get from a solid to a liquid? Like how would you get from an ice cube to water? You would have to put heat into the ice cube to make it change to a water. Okay. On the other hand, if you were going from a liquid to a solid, if you had liquid water and you wanted to make ice cubes, that's an exothermic change. You need heat to leave the water in order for it to become a solid. So let's look at these names. Going from solid to liquid is called melting. Going from a liquid to a solid is called freezing. Hopefully those words are familiar to you. Going from a liquid to a gas is called vaporization. That is perhaps a less familiar word. Vaporization includes boiling, but it also includes evaporation. So we have to have a different science word that incorporates both of those processes. Condensation is the opposite of vaporization. Condensation is something that you might be familiar with if you have a ice cold drink on a hot day. Then the outside of the glass gets sweaty, water droplets form on it, and that's water vapor from the air condensing into a liquid on the outside of your glass. Going from solid to a gas directly, just skipping the liquid entirely, also has a name. That's called sublimation. And if you've ever seen dry ice, frozen carbon dioxide is called dry ice. That sublimates directly from a solid to a gas. And the opposite process to sublimation is called deposition. This is probably the least familiar of all of the processes, but of course the process of making dry ice, the factories that make dry ice would have to do deposition, taking carbon dioxide gas and going directly to a solid. So these phase changes, as I said, all result from absorbing or losing heat energy. And remember, heat always moves from a high temperature to a low temperature. These examples, these phase changes, are not chemical changes because the substance stays the same. In this example, I was using water as my example. In every single picture, we have H2O. The identity of the substance is not changing. However, the distance between particles is changing. We looked at those pictures of solids, liquids, and gases. So the distance between particles is changing because the strength of attraction between the particles is changing. If you have a high temperature, that means high speed, which means the distance between particles is also high. And therefore, the force of attraction between the particles is low. We can switch that statement and talk about low temperature means low speed, which means small distance, and that gives more opportunities for particles to be attracted to each other. So, heating curves. Heating curves show how temperature and phase of a substance changes as heat is added. You've hopefully completed the activity that I gave you about heating curves, so hopefully you're familiar with this already. But there are 5 regions to this curve. We have heat added on the x-axis. So as we move along the x-axis, more and more heat is added to the system. And we see temperature on the y-axis. When we start with a solid, and for the sake of argument, I'm just going to say that this is water. If we start with solid water, if we start with an ice cube and we start heating it, we see the temperature of the ice cube increasing right up to the point that the ice cube starts to melt. And then the temperature stays constant until the ice cube is totally melted and completely liquid. Once we have liquid water and we're continuing to add heat to it, then the temperature of the liquid increases right up to the point that the water starts to boil. Once the water is being vaporized here at the boiling point, throughout that period of time, we're continuing to add heat, but the temperature does not increase. The temperature doesn't start increasing again until all of the liquid water has been converted to gas, and then the temperature increases again. So, along those sloped lines, you either had a solid or a liquid or a gas, and that solid, liquid, or gas was getting hotter. Along the plateaus, along those flat regions, phase changes were taking place. Heat was being added to the system, but the temperature did not increase. The reason the temperature doesn't increase is because of those forces of attraction between particles that we were talking about. The energy goes not to making the particles move faster, but just to kind of break apart those forces of attraction that were holding the molecules together. I hope this helped.